Hello everyone, I'm going to be talking about oscillations today, and basically oscillations has a mixture of circular motion work and a couple of new different things you're going to learn in this chapter. Okay, so I'm going to first talk about the equations you need to know, and basically here we have three different equations: your displacement, your velocity, and your acceleration equation. And you can find these equations out by differentiating the equation above it. So for example, if you want to find out your velocity, you need to differentiate your displacement, and by differentiating your displacement you're gonna have a negative sign afterwards, because the differential of cos is negative sign. And if you differentiate your velocity, you're gonna have a negative sign as well, because the negative of sign differentiated is negative cos. Basically, if you only have the top part and you want to find the rest, it's easy, because all you need to do is you just need to differentiate this first equation, and that's it, and you get the rest as well. You also have your max equations as well, and basically these max equations are the exact same sort of equations as the ones at the top, except the only difference is you don't have your cos omega t, for example, here, and here you don't have your sine omega t, and here you don't have your cos omega t as well. And that's literally the only difference, and these are the maximum equations, so they only work for your maximum values. You also need to know some other equations, and these equations come from the circular motion chapter. They're exactly the same, they don't really change, and they're pretty much like 2 pi f, 2 pi over t, t equals 1 over f, and f equals 1 over t. It's exactly the same, it doesn't really change, and you can use them to find out the different things you need to know, like omega, for example, or t, and that sort of stuff. However, you also need to know a couple of different equations as well, new equations, and these equations are only for this chapter. So these are the equations. You have a equals omega squared x, you have a equals f over m, it's exactly the same as f equals ma, and here you have omega squared equals k over m, where k is your constant. Okay, I'm going to be talking about the different oscillation types, and basically these two different oscillation types are free oscillations and forced oscillations. Now the difference between the two is that free oscillation is basically the oscillations of a body where a system is moving at its own natural frequency under no external forces whatsoever. So for example, it's when you're like not interfering with the system at all when it's oscillating. So you're not giving it a push, you're not pulling it, you're not doing anything, you're not touching it. However, a forced oscillation is like an oscillation that's imposed upon a body or system getting pushed or pulled due to an external force or something. So for example, you're like a swing, you pushing a friend on a swing, that's a forced oscillation, because you're actually giving them energy, and this energy is also increasing the amplitude and stuff. Okay, so basically I'm going to be talking about simple harmonic motion now, and basically the definition of simple harmonic motion is when a body is accelerating proportional to its displacement and the acceleration is acting towards equilibrium position. An example of this can be a pendulum oscillating. When the pendulum is swinging from side to side, its acceleration is at its maximum value, since it's most further away from its position and it has its most energy at that point. But every time it passes the center, its acceleration is zero, because there is no energy at that point. Other things you need to know about simple harmonic motion is that it has a restoring force, okay? And the equation for the restoring force is F equals minus kx. And this is the exact same equation as the spring constant equations, which is F equals kx. The only difference is it's all going the other way, so it's minus. It has a minus sign in it. It's also made out of a time period, and basically the time period is the time to complete one full swing. And again, a good example of this is a mass attached to a spring that's oscillating, for example. Okay, now I'm going to be talking about the different graphs that you need to know. First of all, this is your displacement time graph, and this is your ordinary cost graph. As you can tell from the equation that we have over here, it's a cost, it has a cost in it, and it has no negative or whatever, so it's just your cost graph. So here it is. However, if you go to your velocity time graph, it's a minus sign graph. And basically the reason it's a minus sign graph is after you differentiate your displacement, you get a minus sign equation here, so your velocity is minus sine, while your acceleration time graph is minus cos, because after you differentiate your minus sine graph, after you differentiate your minus sine equation, sorry, you're gonna have minus cos. and this is why you have your minus cos graph as your acceleration time. Okay, so I'm going to be talking about resonance right now, and resonance is made up of two things pretty much: natural frequencies and vibrations. Pretty much resonance is the tendency of a system to like oscillate with greater amplitudes at some frequencies than others. Okay, so, while like a natural frequency is the frequency at which a system tends to oscillate in the absence of driving or damping force. So basically resonance is when you have an object that's at its maximum amplitude while it's oscillating. And natural frequency is the frequency which any object in the world has. Every single object in the world has a natural frequency. Basically, any oscillating system that has a natural frequency when left on its own, this is the resonance. And if a system is forced to vibrate at its natural frequency, it will absorb more and more energy, thus increasing its amplitude, and this is also called resonance. This is pretty much an explanation of how resonance pretty much works. Some examples of resonance include a washing machine that's vibrating sporadically, and like a car, for example, that's also vibrating like crazy. These cars, the car and the washing machine are usually at their highest amplitude when they start vibrating like crazy, and this is pretty much an example. They're both examples of resonance at work. Okay, so basically I'm going to be talking about damping now, and damping is when you damp the oscillations artificially over time, and this suffers loss in energy each and every oscillation. This consequently leads to a decrease in amplitude over time, and what happens is you end up having a graph like this, that you can see that the amp displacement isn't at its highest points anymore because they're slowly decreasing over time, and this is what damping does to an object. It decreases the amplitude when it's like facing resonance, for example, and you can see it particularly in like suspension of bikes or pulling a spring with a mass on it through like thick oil, and basically even a pendulum like facing air resistance, it's also facing damping, because air resistance is lowering the amplitude of the pendulum in simple harmonic motion.